Today we're going to talk about CLF, the concurrent logical framework. Finally, putting all the pieces together that we've put into place, the forward chaining, the backward chaining, the monad, and so on. And we'll do some example programs. Also wanted to remind you that assignment 5 is due today. I've asked that you email me a PDF, or if you're doing a project, the project proposal is due today. So I've already gotten a lot of them, so most of you are aware of that. Assignment 6 will go out today, and the way I'm going to do it is I'm going to add a couple of more questions to the list of questions that I gave out last time. And so you can do either one that you haven't done yet, or you can do one of the new ones. Okay, if you're not doing a project. If you're doing a project, then I'll request do a week from today, or progress report if it's a project. Okay. Other questions about that, by the way? Seems to be going okay since I've gotten a lot of emails. Okay. Like even hours before it's due, so I'm not really used to that. But okay. All right, so today we'll talk about concurrent logical framework. So let me remind you first about the forward and the backward chaining, and then we'll see what we're missing in order to get to a logical framework altogether. Okay. And then we'll talk about the C, what we're talking about when we say concurrency in this context. Okay, so I'm going to use the letters A for asynchronous, and I'm going to use S for synchronous. Okay, because that's a tradition in the way that CLF was defined. But you can also think of the asynchronous as being negative and the synchronous being positive, okay? Except that the plus and minus symbol there can be confused with modes, and so therefore I'm just going to write A and S today. And you can, every A is negative, every S is positive. Okay, so what I'm trying to identify now is sort of the largest fragment on which the kind of thing that we've done so far makes sense. Okay, so the asynchronous ones. Okay, so we have negative atoms. We have synchronous arrow asynchronous. Okay, we have A1 with A2. We also have top. Okay, but I'm not going to write that, or I'm going to write it in a separate place, because top is actually not supported in the CLF framework. Okay, as I'll explain why that is the case. And then we have universal quantification, and I'm going to write it like this: pi x colon a1 dot a2. Okay, and I mentioned before that this corresponds to a universal quantifier. Except what we're going to do is, instead of having a separate category of types, we're going to reuse propositions as types. We already saw that idea that propositions can be types and types of propositions. And there's really no need to invent a separate category of types. And that gives you some added expressive powers, because now you can talk about proofs of propositions in the framework. Okay, so you can talk about those when you quantify over them. Okay. And then the last thing we had was a positive proposition inside a monad. Okay. And so then the positive propositions, so this minus positive. Okay, so we had positive atoms. Actually, let me write up here the ones that we don't support, which is true up here. Okay, so here we don't actually support positive propositions in the framework. Okay, so it's not going to come into this first line, and this is mainly historical, because when we designed CLF, we didn't, in some sense, go all the way. It turns out that in practice you can get by without having positive atoms. But sometimes we wish we would have them in order to express certain properties, but we don't have them in CLF. Okay. So that's what we have. What is positive? We have tensor, and we have 1. And what are some other positives? Plus. Okay. So I'm not going to write that here. because for other reasons we decided to leave out disjunction and 0 from the framework, and I'll explain those reasons a little bit later on because they have to do with concurrency. Okay. What else is positive?
You have an analog to the existential.
Right, so we have an analog to the universal, which is an existential. Okay. What else is positive? Persistence, right? And I think I mentioned this last time. The bang is positive on the outside and negative on the inside. Okay, so it's going to be bang A. Okay. Okay, so let's, in the logical framework, we also have affine assumptions because we got rid of top and we got rid of 0. So we need affine assumptions, so we have the modality affine of A, okay, which you actually got to explore in the homework, so you know what it is. Okay. Actually, no, it was the exam, right? Yeah, nothing like the exam pressure to actually invent something completely new. Okay. All right. So we're almost there. Okay. So let's think about if you do pure backward chaining. Okay, then the sequence that we're looking at looks something like this. We have a gamma, we have a psi, and we have a delta. And this consists of A's, this consists of A's, and this consists of A's. Okay, so these constitute your programs because these are the ones that have implications. Okay, and this is persistent. This is affine, and this is linear. And on the right-hand side, we're trying to prove a negative atom because we're doing backward chaining. Okay, so over here we have a P minus. Okay, and now we need to just go through and figure out if we focus on one of these A's in a context. Okay, can we stay in this class of stable sequence which looks just like that, right? So if a stable sequence that we reach has again that form. Okay, so we have to go through this here. Okay, so if we focus on a negative atom, that's okay. It'll only succeed if it matches the right-hand side, but we stay within that class. If we focus on a width, okay, we continue to focus either on the left or on the right. So inductively, we stay within the class because now we're focused on an A or an A in either case. Okay, if we're focused on a linear implication, okay, then there's going to be two subgoals. One is going to be focused on A on the left. And that's okay because we're still in the same class, focused on something asynchronous on the left. Or we're focused on S, okay, on the right-hand side of the sequent. Okay. Now we have to break that down because it doesn't have to have that form. It doesn't have that form. So if we're on the right in focus and we have a tensor, we break it down and we're now focused on S1 and S2 and we continue to be in focus. If we're focused on 1 on the right, what happens?
As long as the contexts are empty, we succeed.
Right, we either succeed or fail. Okay, we succeed immediately if the context is empty, and we fail if we cannot make it empty. Okay, and remember we have to temper the statement a little bit by thinking about resource management, but that's essentially what happens for 1. If we're focused on an existential on the right, what happens? We have to come up with right. The right rule for existential requires you to find a witness. But from what we saw last time, or time before last, in backward chaining, instead of actually determining a witness, we instantiate with a meta variable or logic variable or whatever you want to call it. And then we continue our search and try to find what that is. Okay, so we already know how to do that. Okay, so we'll stay in that class because the subgoal will still be focused on S. Okay, we come to bang of A. What happens in that case? We lose focus, and now A is on the right-hand side. Where on the right-hand side, it's not a negative atom, but we're not done because A on the right-hand side, a negative thing on the right-hand side is?
We could use invertible right rules.
We have to use the invertible right rule. We're in an inversion phase. So we have to break this down until we can no longer invert. Okay. So let's check. If we had P minus, well, we would be done, but that's okay because that's allowed here with our invariant of pure backward chaining. If we do this, then there's going to be an S on the left and an A on the right. Now, S are positives on the right, so they should decompose, okay, asynchronously, and so should A. So we should be invert on both of these. Here we invert both of the sides. Okay, and here is where we're not allowed to continue, okay, because if we're trying to invert that, we would actually stop with the judgment S lax, okay. So we would actually get to forward chaining. So in the pure backward chaining phase, this would not be allowed, okay. Okay, now one other thing is that you can be a little bit more free than we have been so far. You can also allow just A here. Okay, because if you're focused on the right and you hit an A, then you lose focus and now you invert. And we just already checked that inverting now is okay, according to this grammar, as long as we don't have this. Okay. Okay, and it's become sort of tradition here to write this as down of A, rather than just doing an inclusion, except the down doesn't really have any logical contents. It just tells us we're looking at something that looks like a synchronous formula, but then we come to an asynchronous one. Okay, and so that makes it explicit that we're switching up to here. Okay, so this is pronounced down of A. Okay, so what this means is the pure backward chaining fragment is anything in this grammar, okay, except for this. We didn't check these, but they also check out. Okay, the ones that are not in CLF. Are we okay so far? Pure backward chaining. All our stable sequence, if we start with something like this, all our sequence will continue to be stable all the way through proof search. You okay with this? Okay. Now, what's the pure forward chaining fragment? Where we only do forward chaining. Well, what does the sequence look like? The pure forward chaining sequence would be the same gamma, the same psi, the same delta, and the right-hand side would say S lax, and that S is something positive, okay? Because as I talked about last time, when you have something like this, that gives you the license to forward chain, because you cannot prove truth from lax truth. You cannot forward chain in this situation. You can only forward chain in this situation. You cannot backward chain in this situation because when you come to focus on P minus at the left, it doesn't match the right-hand side because there's no atom there, and so that forward chaining, backward chaining here on anything in any of these three contexts will actually fail. Okay? Okay, so pure forward chaining. Now we would see what is the pure forward chaining fragment. Okay, so we have to go through the whole exercise again. Anybody have a guess what that is? So pure backward chaining fragment is almost all of this except for that. Okay, what's the pure forward chaining fragment?
Probably don't want the down arrow.
No, actually the down arrow is okay. The only thing you have to exclude is negative atoms. Okay, so we'll just exclude that. If you exclude that, the negative atoms, then we get the pure forward chaining fragment. Okay, unless I made a mistake last night, and that's always possible. Okay, but I'm pretty sure that that's the case.
So if you exclude that, everything bottoms out at 1, right?
If you don't have positive atoms, yeah. Right. Right. So pure forward chaining is weird if you don't have positive atoms. Right. Okay. So this seems to be fairly robust thing. Okay. And almost all of it is allowed when we do pure forward and backward chaining. And because we have the monad to isolate the two from each other, we can mix forward and backward chaining. We should always know what it means. Okay. All right. So, so the big difference from what we did so far and what we're going to do with the logical framework is that we have a notation for proofs. Okay. So the difference between a logic and a logical framework, between a logic and a type theory, is that in a type theory you have explicit internalize the notion of what a proof is. And in the logic, you usually just talk about the propositions and when they're true. So what we have to do in order to derive from this a type theory is a notation for proofs. Okay. So we don't start from scratch because we already have developed previously, when we did natural deduction, a notation for certain proofs, like lambda expressions, like, function, abstraction, application. What else do we have? We have let x1 tensor x2 equals m in n, and a few things like that. We'll just need to see how it maps onto this. Okay. And the added complication or the difference to what we did before is that we have a particular restriction of what the grammar looks like, which actually also changes the way that you do the proof term assignment. Okay. And the proof terms are very important because what happens is in a logical framework, when you want to represent computation, so far we have just got an output like, we say we do a computation, but the computation itself is not reified as an object. So when we do substructural operational semantics, for example, we write down a whole bunch of rules, and they can be written in this, okay, which I've shown you actually a few weeks ago. And then you can run it, and it can give you a final value answer. But the computation itself that it performs as it works, that computation is not available to you if you're working in the logic, right? In the logic, you only get the answer, yes, we have reached saturation, or we have reached quiescent, and we have computed this particular value. But we want to reason about that. We want to reason about the structure of the computation that's being performed. And in particular, we're interested in identifying if there is concurrency available in the computation, if the computation is something very sequential, or if things can happen in parallel. And we want to be able to analyze that by looking at the structure of the computation. And so in order to be able to get that, we need to assign some proof terms to these so that they're objects that we can easily talk about. Okay. So that's our goal for today's lecture. We want to assign proof term to these so that we can talk about computation, particularly recognize concurrency, okay, which actually was the starting point for the development of all of this. Okay. So we have a bunch of different judgments. These are only the ones for the stable sequence, but there are also sequences in between that we need to worry about. And we make some kind of assignment. Okay. So we have to work our way through these. Okay, so one reasonable way is that we could start from this judgment here, okay, and see what kind of auxiliary judgments we need. Okay. So in this judgment, actually, I'm mostly going to ignore gamma and psi for the talk on the blackboard, okay, just to be able to have to write less, okay, not because it's inconsistent with anything that we have to do, okay. So we have delta RL, okay, and we want a P minus, and we want to find a proof term here, okay, which sort of records what the proof actually does. Okay, so somewhere we need to keep track of what the different ends are. Okay. So what is the more general form of this? If we don't look at the specific case where it's a P minus, would be n colon A, right? So that's the first generalization. Okay, so let's do some proof terms for that, just so we can get off to a reasonable start. Okay, so if it's S arrow A, okay. Okay, what would be a reasonable proof term assignment for that? Lambda, right? But there's a twist. Okay. But okay, let's start with that. Lambda x dot n colon this. if in delta x colon s proves n colon a. Okay, so that's an s here. Okay, so we'll come back to that because this is actually not very convenient, it turns out. Okay, even though it seems completely natural, we see it doesn't work out very well. For the width, what should be the proof terms for the width? I should write these terms down somewhere. Maybe you guys have internalized this by now, so I'll write it down here. So far the n's are, okay, lambda x dot n. Okay. What do I need for the width? Pair. Do I have to write it out? Probably not, right? You can write that rule. So n1 pair n2. So that takes care of this. For the universal quantifier, okay, we should think about that. So we have delta, and we have pi x colon a1 dot a2. Okay, so what happens there? How do we represent the proof of a universal quantifier in ordinary logic? What's the proof of for all x colon tau dot, let me write here, b, which may depend on x. What's the proof of that look like? Right. So we have to prove b of some y, let's say. Or by renaming, we could say, well, we can reuse the same x. Okay. And we had a context psi here. And we add x colon tau to psi. And so then what would be your proof term for that? Lambda, okay. So this would be some kind of n, and this would be lambda x dot n as a proof of that. Okay, so it's a function which, if you give it an argument, gives you back a proof, an argument m gives you back a proof of b of m. Okay. Okay, so that's, we did it here. So the natural thing to do is do the same thing. So we actually need to make gamma explicit here, because x colon a is going to be unrestricted in this rule. And we get n colon a2, and here we get lambda x dot n has this type. Okay. So it's a function. So this can depend on x possibly, just like in the quantifier case. So it's a function if you give it an argument m, which has type a. Then it gives you back a proof of a2 where you substituted m for x. Okay, so that's what's called a dependent function type. So we have two occurrences of lambda, okay, and that seems to be okay because both of these things are function. This is a linear function, and this is an unrestricted function which puts its arguments in here. Okay, so now we have to move on. Before we actually, okay, so now what happens when we come to a negative thing? I mean the negative atom. Okay, so I should put here, we have another lambda, actually it's already there, so, okay. So when we come to a negative atom, let's just think about the backward chaining fragment. Not that it matters much. How do we proceed in the proof now? Well, how does backward chaining proceed when we see a negative atom on the right-hand side? We have to focus on something in delta, right? We have to focus on something in delta, or in gamma, or in psi, if we make all of these explicit, right? Either using a copy rule, or just taking something out of delta and focusing on that. Okay, so let's just look at it like this. We have delta, and we have x colon a. Okay, then we're in delta. And now we're focused on A. And we're still trying to prove P, okay? And we have to think about what goes in here, okay, for this proof term here. But I'm just going to actually say whatever proof term we synthesize there, I'll put that same proof term here, okay? We'll see what these R's turn out to be, but we need them here. And roughly you can think of that for every type of judgment that we have to consider, we'll need a different type of proof term, okay, just so we don't confuse these different situations. So here we're considering focusing on the left, so we need a new kind of proof term R. Here we have focusing, here we have inversion on the right, so we have these normal terms N, okay.
So the R's are, there's an injection in R's in there.
Right. So because we have this situation here, okay, an R will have to be considered an N. And we might want to think about whether there would be an arrow that we would use to decorate that, okay, eventually. Just like this. Instead of just writing an inclusion, we make explicit there's a change of phase, okay. Okay, so now we need some left focusing rules, okay. So let's think about, let's see, which one? See what happens when we're focused on a negative atom. Okay, so we have some delta, and we have a negative atom, and we're trying to prove a negative atom. Okay, there's two cases. They're either the same or they're different. Okay, if they're different, do we have to worry about a proof term? No, because we cannot finish the proof because we always fail, right? So that's a big thing about focusing. But if they are the same, okay, so if we're back to the identity rule, okay, which is on brackets, okay, so what do we do in that case? Well, we want to return whatever is our evidence for this thing over here, okay. So we have accumulated some R over here, and we just return that as the proof of P, okay. Okay. And we know that delta has to be empty in that case. What about gamma and psi? Do they have to be empty? Okay, unrestricted assumptions don't have to be empty. Affine assumptions don't have to be used, so they could be left over here. So want to be explicit about that. We write it like this. Okay. So what's emerging here is the following thing. When we make new assumptions, it's always at a variable. But when we're focused, the evidence for the fact that the thing we're focused on is true is not going to be a variable, but it's going to be some kind of term R in that grammar over there. So what does that tell us about? We already know one kind of R that must be in existence here.
Just the plain variable.
It must be a plain variable because if we always have an R here at this point, we must have a variable. So a variable must be a possible form of an R. Okay? All right, let's look at the rule for focused on implication on the left. All right, so we're in delta, and we have an R, which is evidence for S arrow A. And we're trying to prove P minus on the right-hand side. Okay. So what is the rule for focusing on an implication on the left? Two subgoals, right? Okay. So one is, the first one is, okay, except that we're doing backward chaining here. So the first thing we do is not S, but the first one is A. Okay. So we have A in focus here. Okay. And then the second one is, whoops, I didn't leave enough room there. To prove S in focus on the right. What about the resources? they get divided. And the reason, oops, need some room here, that this is going to be okay is because I'm going to use resource management, so I don't have to decide at this point, but I put everything to here, and then whatever is remaining is going to be used to solve the subgoal over here. What is my goal over here? The succedent of the sequent? P minus. Okay. Let's see, what else can we fill in? What's the evidence for the fact that A is true? You actually did this in a homework exercise, I believe. So how do we get evidence that A is true? So we have R, which is evidence that S implies A. How do we get evidence for A?
Apply to evidence for S.
Yeah, we have to apply to evidence for S. And so we need that here. So we need some M, which is evidence for S. And then we take R, and we apply it to N. See, there was a reason for everything that I asked you to do. Okay. So here is 1. Okay. Okay. So this is good. It's a little bit weird because there is something that in the modes that is a little odd here, because you solve this one first, but you don't get the term N until you're done with this at the end. M, actually, sorry. M. So the way that the proof terms are propagated is different from the way in the order in which you do proof search. So, but you know, you have to convince yourself that it really is possible to do it that way. Okay. And so then what do we do with the term here and here?
It should be the same R prime.
Right, because the P doesn't change, it should be the same term, right? This is going to be our R prime, which is a proof of P, and we'll just return that over here, okay? There's nothing we need to do about that because we already have it here, right? In the left rules, the problem is to find a justification for your hypotheses or for your antecedent, and not to synthesize a thing for the conclusion, just carry that through, okay? Okay, so that's a tricky rule, okay? Okay. What else do we need at this point? So we have, so here we have R applied to M, and M is something new, right? M is when you're focused on something positive on the right-hand side. Okay, so that's what an RM will be. Do we have anything else yet? Don't think so. So what happens when you are focused on a pi? Sorry. If you're left focused on a pi and you're trying to prove AP minus on the right. So how does that work? So think about, you have a universally quantified clause in your context and you're focusing on that. What happens to the universal quantifier? Yeah, you have to instantiate with the fresh variables, just like the existential before on the other side, right? You don't know what it is, you put in a fresh variable. In this inference system, okay, where does that variable come from? Well, you guess it. Okay. So we have, in the empty context, is it N that annotates an A? Yeah, N is the thing that annotates an A. And then what are we focusing on here?
A2 with N for X.
Yeah, A2, where we substitute N for X. And we're still trying to prove P minus. Oops, I need more room here. So what is the evidence for this being true? Okay, so we have some evidence R for this. And so if this is going to be realized by a function, right, which takes an x of type A1 to an A2, then this is going to be a function application of R applied to n. Okay? So we have one more case. Because we have a kind of a hidden lambda in this, we also have R applied to n. We'll see if we'll need that, okay, or not. Okay. So operationally, what happens is because there's a dependence of A2 on x here, what you do is n is actually not going to be a term which you know ahead of time, but n is going to be a variable that you use. Okay. And so the reason that we always know that we get the end in the n here, get the n in the end, okay, is actually just because we did mode checking on our code before. So if we didn't do that, we wouldn't actually know that we'll really get a valid n here. Okay, so the reason that this rule is okay is rather subtle. Okay. Did we do everything now in that up except for the braces? Okay. So let me first do the pure negative fragment first before I move on. Okay. This one here? Oh, this one, yeah. Yeah, it would be R prime. It doesn't change, right? The right-hand side does not change in these rules because the inference rule is applied on the left. Okay. Why did I make this context empty?
It's an unrestricted resource introduction rule.
Right. So this thing is like a universal quantifier, which makes the assumption that we make unrestricted. Okay. And so therefore, you cannot use any linear resources when you use that. Okay. The fact that this is actually unrestricted and this is empty is a significant problem on occasion in using the concurrent logical framework. But when we originally designed that, Eliano and Kevin and I were working very hard to try to figure out if there's some way that we can have a quantifier here where this term n doesn't have to be unrestricted. And we could still have some dependency, but we're unable to come up with something like that. It took another 8 years or so until Jason Reed figured out how to deal with that. And I'll talk about that either in the next lecture or the lecture after next, depending on how far I get today. Okay. But in the CLF technology, we don't have that available, Jason's solution. So what we do instead is we'll just say this has to be closed. No variables in it. Okay. Okay, so what's actually open now is this judgment, right? In delta, so what we have is R is of type A, proves R prime colon P. And what still we have to define is when we're focused on an S, and what did we put there? A M. Right, we still have to define that. Okay? All right, so how do we do that? So we need to look at all the S's and see what are natural proof terms for them, right? Okay, so if you have a tensor, we already know we're going to have to split things up. S1 tensor S2 in focus. So we get delta 1 and we get delta 2. And we get an M1 here, and we get an M2 here. And so that means here we just get M1 tensor M2. Okay? So this is just the same thing we did before in natural reduction, except that now we require this thing to be in focus, okay? Which before in natural reduction didn't make much sense. So one M's we have is M1 tensor M2. Okay, what about 1? What is the proof term for that?
Just require the context to be empty.
We require the context to be empty if we're focused on 1. And anybody remember the proof term notation we had for that, which was a homework exercise? Okay. Since we mimic here the constructor, we'll mimic here as well. We'll just write 1. Okay, so we have a 1 over here. Okay, so for the existential, it gets a little bit tricky. Okay, so if we focused on the existential, and then we have another S. What's the proof of an existential?
Providing like an object that's satisfied.
Okay, we have to do two things. We have to provide an object that's satisfied. I think that's called an A, right, in our notation, an N colon A. And for the same reason, which I haven't fully explained, at the universal quantifier, we require this to be closed. Okay. And what is the second part of this? So we have some delta. Okay. What's the proof of now?
S with N for X.
Right. We have to prove the instance S with N for X. And that gives us some M. And so here we have to return a pair of the N and the M. Okay. And I think the notation that CLF uses is N comma M like this. We could have also written a tensor there because it's very much a special case of this here. So maybe on the board I'll just write N tensor M. Okay. Okay, so here we have the special case of an N tensor M. So that gets us through to here. For bang, what happens there? If you're focused on a bang on the right-hand side,
The context must be empty.
the context must be empty. So we're focused on, oops, I need room for the proof term. We're focused on bang A on the right-hand side. And so what happens there?
Just prove an N colon A.
Right, we lose focus. So we prove A, call that N, which is in the empty context. And here, the proof term notation for that was bang N. So there could be a bang N here. For the affine A, can anybody guess what that would be? Nobody's willing to guess. Okay, affine N. Okay. So what happens there, the linear context still has to be empty, but we're allowed to have something in the affine context, right? And then we call the term constructor the same as we call the proof constructor. See here underneath there's an A hiding. Okay, so we have to prove that A, and the proof of that will be an N. Okay, for the downshift A, what actually happens? So we're looking at something like we're proving in a delta. Down A in focus. A is negative because there's a down here, which is a conversion from something being negative to something positive. So what happens in that case? We lose focus. And then we prove A. That gives us an N. And then the proof term of that, if you want to be explicit, would be down of N, right? So it would be down of N in here. Okay. And if you look at the papers about CLF, you know, this was an inclusion, so there will be no down here. There will just be N itself. Okay. Okay, it looks like we're making progress. We got this. So with this, we have the complete proof term calculus for backward chaining. Okay. A nice properties of this calculus is that if you think about if we didn't have this over here, and you just look at this particular language, that every term has what we call a canonical form. Okay. Or another way to think about this, if you look at this grammar here, okay, you can't write down any redex. You can't write down for lambda applied to an argument. Okay. Because the only thing that's applied to an argument is an R here. But an R, okay, can be a variable, or it can be an application, or it could be a projection, which I omitted. Okay, but it can't be a lambda abstraction. So the grammar here enforces that you can write down any normal forms, and that actually makes sense because we want to only capture focusing proofs over here, and focusing proofs never introduce cut. Okay, which corresponds to there shouldn't be any redex here. We shouldn't have a lambda abstraction applied to an argument. We shouldn't have a projection of a pair. We wouldn't have a let of one of these things. Okay. So actually, it all fits together in the way that we would expect this to fit together, at least so far. Okay. It's a little bit odd because we have introduction form for tensor and for the existentials here, but we don't have an elimination form, or we don't have let bang. Okay. And the reason it didn't come up is because there is no way that when you're here, you can back to a positive. So we omitted this. In fact, if we had an S here without the braces, okay, then the grammar would essentially collapse because the two pieces would correspond to each other, because you can always go from A to an S and from S back to an A, and then we would have arbitrary terms. Okay. Okay. So because of that, we have constructors for these, but currently no let form destructors. Okay, which is a very nice property to have. Okay, so now we need to extend this in order to capture the forward chaining. So now I need to make some room, unfortunately. Okay. I'll leave these three judgments up. Actually, where does it come up? Okay. I guess in the judgments that we have so far, it doesn't really come up, right? Okay, so, I didn't mean to erase that. That's the one rule I didn't want to erase. Because we overlooked something here. And column A. Okay, so I'm going to get rid of all the other ones. Hmm? Okay. Okay, so the thing we overlooked is that we didn't really have any rules to deal with this x colon s over here, right? The only thing we're allowed to focus on something negative, but we have no rules to decompose when there is something like this in the context. So we need some rules for that, right? So let's look at some of the rules. So positives would be, one rule would be if we have S1 tensor S2 in the context, and we're trying to prove a conclusion A. Actually, the conclusion doesn't matter, but okay, what does it break down into? Tensor left. Yep, it's S1 and S2. And on the right-hand side, we're still trying to prove A. Okay, somehow the right-hand side shouldn't get involved in this because we're just working on the left-hand side here when we're breaking these things down. So the question is exactly how do we capture this breaking down from these two into these? So we can say if we have some evidence, some proof of S1 tensor S2, then the first projection is a proof of S1 and the second projection is a proof of S2, because the projections actually apply to the additives, right? And they don't really make sense here. So we have to have some different way of dealing with that. Okay. So what we're going to do is we're going to actually we're going to guess. I'm going to write patterns here. And the other delta is just going to be carried along. Okay. So we need one more thing over there, which are these patterns, okay, which annotate positive things when they're on the left-hand side. Okay. So this is going to be patterns. And the way to think about that is the way we saw patterns so far is only in a very special case. And the special case was, let me get rid of some of this. When we broke down a pattern, let P1 tensor, actually x1 tensor x2 equals m in n, okay? And the idea was that m could be of type A tensor B, and that x1 would be of type A and x2 would be of type B while you check n, right? So that was the rule we had before. And now we're generalizing this here from this one-stage decomposition to allow patterns here, P, okay? So that if you have something here which has A tensor B tensor C tensor D, because these get always broken down together when you do focusing, there's no place in between. Instead of having just a binary pattern over here, you can have some arbitrary pattern over here. So at some point you would expect to show up in this language something like, let P equals M in N, where this is one of these patterns, and this is something like A tensor B tensor C and so on. So perhaps we should just say this should be like some kind of an S, right, which you break down into the pieces, okay? And these should be broken down all the way until all the components are no longer S's, so that they're A's, so that they're allowed to occur in the context, because A's are the things you can focus on, and A's on the left-hand side are no longer invertible. So that's what you want to accomplish. So let's see what happens with that. If we have 1 on the left-hand side, and we're doing inversion. Oh, by the way, what happens here? Should just carry down, right? So if this is n, it should just carry down, right? Nothing should happen here. If we're looking at 1 on the left-hand side, what's the 1 left rule? It just goes away, right? Okay, so what would we call the pattern here?
1.
Yeah, so we call it 1, so it matches the constructor. So 1 colon 1, there's nothing here, and then we get n here, and we get n here, right? So we have a possibility of patterns now. P1 tensor P2 or 1. What would be the pattern for bang n? Okay, so let's look at that. So we have delta, and we're looking at bang A while we're trying to prove okay, let's say A prime over here. So what happens with bang A? When you're doing inversion? You have bang A on the left. What happens during inversion? Right, we move it to the persistent context. So we have a gamma here and a psi here. So we move it into here. And just, okay. So we can already predict this is going to be n. There shouldn't be nothing happening here. Okay. Now when we move it to the persistent context, in the persistent context we're only going to have variables. Okay. So let's call this x. Well, actually, what did we call persistent variables? U, right? Right, we usually call them u. Okay. So what would we expect as the pattern here? Bang u. Okay. 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 So if we distinguish the persistent variables from the linear ones, then we have one other kind of R. Because we can focus on an unrestricted assumption, okay, and the justification for that would be U. Okay? We can also focus on an affine assumption, right? Moving it into the linear context, so they could also have an affine variable here. Okay. Okay, what other patterns would we get? What pattern would we get from here? At A. And what pattern would we get from here? Down X. Okay. Okay. So, okay. So now let's get back to this here. So what happens in this rule? What is our proof term assignment for linear implication? Right. We actually abstract over a pattern, which means that all the variables that occur in the pattern are going to be bound variables, okay, in the body here, and they can occur there. Okay. So we're abstracting not just over an X, but we have a more general form abstracting over an arbitrary pattern. Okay. This doesn't show up so much in here, but if you be careful, if you think about this carefully, so in delta, what can happen? In delta, you can have variables x colon a, or you have patterns p colon s. Okay, which we didn't think about before. When this sequence is stable, you will never have any pattern variables left. You only have x colon a, right? Because in the inversion phase, you're supposed to eliminate all the synchronous connectives here, all the positive connectives here, and get it down all the way down to a's. And that's always possible. If you look at the grammar, you see that this will actually happen. Okay, so one of the reasons we don't have disjunction and falsehood, well, there's multiple reasons not to have falsehood, but for the reason not to have disjunction is that this simple story no longer applies, because what happens is that if your proof splits into two, okay, then you have to have a pattern like P1 plus P2, where P1 makes sense on one side and P2 on the other. And then there will be a proof term N1 coming from the first premise and N2 for the second premise, and you have to somehow combine them, something like this, okay, on the right-hand side. And that's really odd, because P1 occurs only in N1 and P2 occurs only in N2. But you cannot see this locally because we don't have a way to redistribute these things. So we either have to find some way of redistributing these things, or we have very strange proof terms where bound variables are somehow in a complicated way related to their scope. Okay. So there are other reasons, as you'll see, but this was one of the complications, is that it's hard to find a good proof term assignment that works well as a notation for this kind of focusing system.
Do we just have like a U tensor P pattern for existentials?
Oh yeah, right. So the last thing here is we need to model that, and that would be written like that. Yeah. So it should really be, strictly speaking, a slightly different constructor, so you can distinguish those two cases. So maybe just to be clear about that, I would say, let's write it as a pair like this. And then this would be the pair n comma m. Okay. Okay. Yeah, what actually happens in the implementation is that the tensor and the existential quantifier are kind of unified as a construct. So both of these are written with brackets, okay, or can be written with brackets. I'm not 100% sure how flexible the syntax is there. Okay. Where's Favonia? He was hacking around with it. What is the syntax? Can you write star in patterns also, or does it always have to be brackets?
But I only multiply the positive when the nested bracket happens in the model.
Okay, right.
In other cases, the process is already powerful enough to
Okay, so the patterns are always like brackets. Is that right? Okay. Yeah, so there will be some little bit of syntax translation we have to do. Okay, so this took me longer than I thought, but I guess there's a lot here. So now we're almost there, okay? But now we need to actually talk about the monad, okay? Because what happens when you go into this judgment, okay? Fortunately, we don't have to start from scratch now. So let me get rid of this. So the main question is, if you're in this inversion phase and you hit the brackets, which is now possible, Okay. What happens at this point? If you're inverting the bracket, talked about this last time. Yep, we're going to lax because we're going into forward chaining mode. Okay, and we call that category E, and we write braces E. Okay, and so E stands for expressions, and so we have a new judgment here in delta E is of type S lax. Okay. Okay, so what are the E's? Well, we'll have to work our way up to that, what they actually end up being. So let's think about this now. What can happen for the E's? What can happen when we're in S lax? So there's two things we could possibly do. One is we can focus on the right-hand side and prove S in focus, right? Okay. We would only do that usually in the operational semantics. We do that as a last resort if we've reached saturation or quiescence and nothing can be done on the left-hand side, right? So that's the semantics that we had. So we can focus on something here as long as it ends in one of these monad braces, okay? And the other possibility is if that is no longer possible, then we can focus on this on the right-hand side. So there is a rule like this. If we have S lax, then we can prove S in focus on the right-hand side. So what's the proof term for that? M. And so here we return M, and maybe there should be some annotation, some arrow on that. We usually don't write one. Not sure what the right arrow here is, actually. Okay, but for the E's, one possibility for the E's is that it is an M. Okay. The other possibility is that we focus something on the left. Okay. Now we already have a way to focus on the left. Okay. So for example, we could take delta x colon A while we're in the monad. Okay. And then we would say delta x colon A in focus. Okay. So what would happen in this case? Well, the right-hand side is still S lax. Okay. So we wouldn't really expect there to be any change on the right-hand side, right? Because we just propagate whatever term we have, E. Okay. Okay, so what is the new rule that we didn't have already? Because we already have all the rules in left focus, right? Most of them. Except we left out one.
Where it's S monad.
Right, if you left focus on that, we left that out because it wasn't possible before because the right-hand side was atomic, right? So that was impossible. But then we have one more rule. We're in delta, okay? We have an R, which is a justification for S in focus. And on the right-hand side, we're trying to prove an S prime. Okay, what happens when we're in focus on the monad on the left? First of all, we can only do that if we're trying to prove something lax, right? But we are, so we're okay now. So we go into S, but we lose focus, right? Because S is invertible on the right-hand side. What's the proof term annotating in S? It's a pattern P. Okay. What do we get out of this judgment here? an E. Whoops. Can't even write an E anymore. Okay. So what we do here, okay. So what we have to do here is, well, R actually computes something which has this type. And this is a pattern. So it turns out that now we have the let form appearing. That braces P equals R in E. Okay, so that has to go in here. Okay, so this R is the evidence for something which is type braces S. And the S will have to match P. The pattern will be a pattern for the type S or proposition S. So that works out. And the R will have the braces type, so that matches these braces in the notation. And P is indeed bound in E, because P is indeed bound in E, has a scope E. Okay, so it all works out in this case. So this is going to be like a let expression. Okay. All right, so we have let P equals R in E. Okay. All right. Whew. Okay, so I think we're done now. Okay. Okay. I think I forgot something here. This should be lambda P. Okay. Okay. Oh, yeah.
But then isn't there also a lambda for the exist that doesn't?
A lambda for all, you mean?
Yeah, that's for all. Or
Right.
would that also be?
Well, in the implementation, it's unified because this is being seen as this is kind of seen as bang A1, arrow A2, okay, in quotes. So it's going to be lambda bang X, and bang X is a pattern P, or bang U actually, bang U, yeah. Right, so according to what we did, it should be a counterpart to this here. There should be a lambda U dot N that somehow corresponds to this kind of application, but in the implementation, those are not distinguished. Okay, okay, so I have 10 minutes, so I think I'm going to try to actually write a little bit of code for this using this, so you can see how it actually works. Okay, so what I was starting with here is actually, this is a pure backward chaining program, the way you'd write it in self. This is for the natural number addition and multiplication. Not multiplication, sorry, natural number addition. So we have nat as a type, we have the empty one, and D is something that takes a natural number and a least significant digit, which is a bit, and gives you a natural number. And then we had the two functions, plus and increment. And so, for example, here, plus m of 0 and n of 0 gives you r of 0 if plus of m, n gives you r. And I think I mentioned in lecture that for backward chaining programs, you usually write the arrow in reverse. So this is called the head of the clause here that's matched against your goal. And this is going to be the sub-goal that's being solved. And there's some mode checking going on if you use plus in the usual way. This is an input, this is an input, this is an output. So because this is an input, you know m. So you know this one here. Because this is an input, you know n, so this one here. So therefore, we can call plus this way. We get R out, and that allows us to construct this. So all these clauses, unless I make a typo somewhere, should be well noted. Okay. So now I actually want to write some kind of a forward chaining program. Okay. Okay. So I want to go back to the lights out example that we had. Okay. So that was also in the exam. So the first one was to check whether they were all out. Okay. So we had some kind of a square where it says either the square is on. Let's see. So what's the best way to do that? So in this case, I'm going to abstract away from the natural number which index it because it actually doesn't matter. So square, so a value is either is a type, and a value on is a value, and off is a value. And a square is from a value to a type. So we have various assumptions in the linear context. There are going to be certain squares on and off, and I just abstracted away from what the squares actually are. So I don't have to write the natural numbers there. Okay. Then we have all out, which is a predicate. Okay. And we have, so how does this work now? How do we check if all squares are out? Anybody remember?
For all x colon value,
Yeah.
square x is of type off.
Square. Okay, so I took away the x's. So if it's off, if the square is off, then what do we generate? Monad 1. Okay. So that would be SQ off. Okay, that would be one way of doing it. Let's see if we can finish this. Okay. So we need to have one rule. What about when the square is on? Do we need a rule for that?
No, because then you just fail.
Then we just fail. Okay. But we wanted at the end to say be able to prove all lights are out. We want that to be the only thing left in the context. So how do we deal with that?
You could maybe say one only all out if you're expecting to get rid of everything.
Just like this as a clause. What do you mean all out
Or I guess SQ.
if you can get rid of everything like this? Okay. Okay, let's see what this would do. Let's just think about this. So this would say you can prove all out if you can go to forward chaining and eliminate everything. Okay. And then we're willing to say everything's off. Does it seem reasonable? It's not exactly what we did in the assignment, but okay. Okay. So let's see if we can actually run this somehow. I can never remember how to do that. Okay. Okay, so we want to say query Bound or number of leg bindings before boarding. There shouldn't be any bound. Expected number of solutions. Don't know. Number of solutions to look for. Well, as many as we can. Number of times to execute the query. Just once will be enough. Or maybe, I don't know, 3 times. Okay, so next thing has to be the type that we're looking for. So what we want to do is we want to put some off squares into the context. And then what do we want to say? We want to ask if all out is true. Does that make sense? Okay. Okay. So apparently it executed. Okay. So x1 is the variable annotating the first one, x2 the second, x3 annotating the third, right? So now we're using that rule that says if you see a square that's off, you can remove it. And so we bind nothing here, right? And then we do this one, we bind nothing. Then we remove the third one, we bind nothing, and then we succeed because we can use the test clause applied to the braces 1 in order to finish. Okay. Okay, we run it a second time. This time it happens to do things in a different order. x1, then x2, then x3, x1, then x3, then x2. Okay. So we'll do things in some kind of an order. Now the observation I want to make here, and that's what I elaborate on in the next lecture, is that if you look at these let expressions, okay, there's no dependency between them. Okay, so you can swap these, and in fact, the 3 times we got 3 different answers. What that basically means is that these rules could have been executed in parallel, and it would have been perfectly okay. There would have been no reason to not do them in parallel because there's no dependency between them. And in fact, if you look at the program, you can see that, okay, because this doesn't generate anything, nothing can wait for this rule to fire first. Right? This rule can always fire if it sees off because it couldn't possibly block anything. So this little program is sort of maximally parallel. Right? All the things can fire. And when you're done, then you see if you've consumed all the assumptions or not, if there's something left. Actually, we should check that, right? If we say sharp query star, 4, and we put a square that's on into the mix somewhere, then it better fail, or we have a bug somewhere. Okay, so it ran it 4 times and never came up with an answer. Okay, so since we didn't say how many solutions are expected, it didn't actually fail to parse, but it actually never gave us an answer. So it does fail each time. Okay. Okay. So, but these things can fire asynchronously, independently of each other. Okay. So actually, a lot of the solutions you had for this particular problem, they were actually sequential solutions. And the way that they worked is you started with something like init, and if you were at init and you saw a square that was off, you generated a new init. And you did that all the way through. And in that case, because you generate a new init from an old one, things are extremely sequential. Okay. So we can implement different kind of algorithms in this way. Okay. Some more concurrent than others. And this algorithm has a lot of this very simple algorithm here. I hesitate to even call it algorithm. Okay. This very simple algorithm here, or the little simple program here, has a lot of parallelism because all the rules can fire independently all over the place. Okay. And so, in the way that it's manifest is that if you look at the result, well, in different ways. You can look at the program, you can see whether the dependencies between the clauses. You can also look at the proof, and you can see that these can be permuted with each other without changing what is being proven. Okay. And if you've actually did that exercise about how you can permute inference rules, okay, this actually becomes relevant here because we're talking about permuting inference rules in order to make 2 proofs equal. Okay. And so actually, with a small change, well, actually, we're not changing, but a small extension will be talked about today. We can actually say that these let expressions here shouldn't really be sequential lets, but they should describe some kind of a graph structure. And the graph structure contains the information about the dependencies about the computation on each other. And that dependency is gives us sort of kind of information how much parallelism there was in a particular computation. Okay. Okay. So we'll do that. We'll do that next time and write some more programs. Okay. And for the next homework assignment, like I said at the beginning, if you're doing a project a week from Wednesday, I expect the progress report. If you're doing the homeworks, you can do any of the other homeworks that you haven't done yet, or you can do one of the 1 or 2 new ones that I'll throw in at the end sometime later today, and then I'll email it out. I'm starting to make progress in the lecture notes, but it's going slowly, but I'm getting there. Okay, so we'll see you Wednesday.